Thank you very much, Mr. Chairman, and first of all, thank you, Alberto, thank you, Dominic, for inviting me to give this talk. This work was done in collaboration with Jason Pelekis, who is a very good student. He's so good that now he's no longer working for me, as you can see, but he's working in Cambridge. So, you know, it's nice when you see your students flying away and becoming independent and abandoning you with your experiments on the web. That's it. Okay, so, okay, what we want to do basically is investigating the mechanical behavior of notched plane concrete under static and dynamic loading. So, notches in concrete, it sounds quite strange in a way, but the reason behind this work is that I'm working, have also a project on 3D printed concrete. So when you 3D print concrete, of course, you can start exploring different geometries, so local stress concentration phenomena can become an interesting aspect. But of course, since when we started, we really didn't know much about this aspect, we started considering simple conventional concrete. So of course, we went back to the literature, and what you can see is that if you define this ratio, which is the dynamic strength divided by the static strength, you test a different material. This is a nice review published back in 1998. You can basically see two regimes, that is, as the strain rate increases, of course, this ratio increases, and when the local strain rate approaches about 1 strain per second, there is a quite evident change in the slope of the curve. But no matter what you do, in the end, in this schematization, so if you consider strength and local strain rate, the relationship between these two quantities can be expressed using a power law. And if you go through the literature, you can find a lot of nice models, very sophisticated, but in the end, from a mathematical point of view, what you really need is a power law. And, okay, we also consider the fracture mechanics aspects, so this is the fracture toughness. Surprisingly, we couldn't find a lot of data, but what you can see here is that a kind of similar behavior. So there is a kind of a knee point, and up to a certain value of the strain rate. And I really don't like this diagram, because what is the strain rate in the vicinity of something which should be, in theory, so sharp to result in a singularity. But, you know, let's take the results as they are presented. And what you can see is that there are basically clearly two regimes. So we started focusing our attention on this initial regime. Okay, so what we had when we started is the theory of critical distances, as it was presented, reformulated actually by David back in 1999. I really like that paper. And the idea is that what you need is an effective stress, and when this effective stress becomes equal to the material UTS, don't forget that this applies to brittle materials, your component should fail. But what is this effective stress? Basically, this effective stress can be calculated in different ways, so you can move a bit away from the notch tip. Actually, this length is equal to L divided by 2, so this is the critical distance value, which is a material property. But also, you can calculate the same effective stress by averaging the stress along a line having length equal to 2 times L. Or finally, you can average the stress over an area, a semicircular area having radius equal to L. And if you go back to, for instance, David's book, you would find this nice formula to calculate L, which is simply based on the plane fracture toughness of the material and the material UTS. So, this is a classic formula. It applies to brittle materials. We know that when we play with concrete, talking about brittle materials, ductile materials, it's a quite dodgy area in that sense. But, you know, for the time being, we are happy with these assumptions, also because the TCD is capable of accommodating material non-linearities into a linear elastic constitutive law, so which is good. So let's try to keep everything as simple as possible. But this approach applies to quasi-static situations. So what we need is being also able to consider the dynamic behavior of notched concrete. So what we did then, one of the big things is that, you know, you can use that formula, of course, but it's not so easy because sometimes it's not possible to determine the fracture toughness. So a trick we use to determine the critical distance is based on the point method argument. So we say that if we have a specimen containing a known geometrical feature, we can of course plot the corresponding stress distance curve in the incipient failure condition, and of course L divided by Q is equal to the stress resulting, which is in turn equal to the material UTS. So that's the trick. So we assume that the material UTS is known a priori, and we can estimate L divided by 2. And this is the trick we are going to use in a different way to estimate L under dynamic loading. Okay, so, but now, as I said, we want to move to the dynamic case. So we know that the failure stress varies as what we call here Z dot changes, where Z dot could be either the loading rate, the strain rate, or the displacement rate. You find different ways of tackling this problem, so this is the general formulation. And as we saw at the very beginning, we know that there exist very complex models, but at the end of the day, what those models do is calibrating a power law. So this is basically nothing but the power law, where Z dot is the variable we use to model the process, and alpha and beta are two material constants. And the same idea applies to define the fracture, the dynamic fracture toughness of the material. So in theory, by running our experiments, we can calibrate these constants, and we can define the sigma f versus z dot relationship, as well as the k1d versus z dot relationship. And after that, you can choose if you want to use the loading rate, the strain rate, or other ways. For instance, here it could be the fracture toughness rate, the fracture the stress intensity factor rate. So if we use these two definitions, of course, we can recalculate L according to the classic formula. And what we expect is that in the most general case, L varies as Z dot varies. Why is that? Because in theory, or in the most general case, as the loading rate or the local strain rate increases, maybe the crack initiation could be promoted by different mechanisms. So somehow this should affect the length we use to apply our model. And we also developed this approach considering metals initially with our Russian friends here, and that's the idea. Okay, so this is what we had when we started. So okay, now we know that we can define somehow our failure stress as the quantity we use to measure the dynamic content of the loading we have increases. And of course we can reformulate the point method, the line method, or the area method according to these two quantities. So basically what we are doing is introducing the Z dot, which could be, as we said, either the strain rate, the loading rate, or the displacement rate. Fine, so what's L here then? L, I'm a big fan of the point method. I don't really like the line method, but I really like the area method. In particular, I like the point method when I have to do my calculations, because it's very easy. I move a little bit away from the notch, I pick up the stress and I manipulate the stress, and you can do whatever you want. But I really like the area method when I have to interpret what I'm doing, because in a finite fracture context, basically we can assume that this area, the one which is used to calculate the effective stress according to the area method, is that portion of material controlling the overall strength of my component. So we need to focus our attention on this area, because it's where the real party is, when we are running our tests. So does this idea apply to concretes as well? Okay, so very easy. We went back to the lab, we prepared the concrete mix, which is a very standard concrete mix, Portland cement, natural round gravel, grade M concrete sand. the water to cement ratio was equal to 0.5, and the bending strength, the resulting bending strength was equal to 5.6 megapascal. So as you can see, something very standard. And this is the macroscopic structure. And why is this concrete good? Because in the end, to understand what's going on, we don't need the microscope, because the macrostructure is enough for us to link what's going on in the material to our predictive approach. And with a bit of patience, we measured also the average interaggregate distance, and it was equal to about 4 millimeters. So in a way, and that's it. After that, we cast a number of samples. You know, we had some cast-in notches, and for the sharpest notches, basically what we did was putting a slit using a saw. So we recreated a kind of crack-like situation. We took out from the cellar an old machine, because I didn't want to modify this machine, and it was very good fun, getting very dirty with the oil, and we basically reused the part of a not-to-Kingston bar. So anyway, so we came out with this strange thing which allowed us to change the basically displacement rate very quickly, so to explore the area we were interested in. And here you can see the results. For instance, this is the unnotched specimens, this is the failure force versus the displacement rate, and you can see a clear strain effect. And the same strain rate effect is evident also for the results generated by considering the different notches. Okay, so here are some pictures showing the results. A conventional mode 1 crack, I would say. It was a very rough material, if you like, and inspecting the samples was enough to understand that there were two processes resulting in the final crack, independently from the loading rate. A crack initiation, which was mainly due to the bonding between the cement paste and the stones, and the subsequent propagation through the cement paste. So this is the reason why, as I said, I really like this material. Well, these are the cracks we saw for the different displacement rates. So after that, since we like to keep things as simple as possible, we used ANSYS to model the stress distribution in our simple specimens. And actually, what we did was very brutal. We assumed that our material was homogeneous, isotropic, and linear elastic. So we completely ignored the presence of the aggregates inside the material. So we calculated everything in terms of stress. This is the function we used to calibrate the failure stress. We used the sharply notched specimens to determine the red curve we need to calculate for any given value of the displacement rate L. We calculated L for different value of the displacement rate, and we got that the L value was constant and equal to 4.8 millimeters. But the distance between, the average distance between two adjacent stones was about 4 or 5 millimeters. So we are in the finite fracture idea. That is, the crack initiates at the stone, it propagates through the matrix. As soon as the length is equal to about the average interaggregate distance, the specimen is gone. So this was the structure, and this is the accuracy of the approach. As you can see, we got very good results for the using both the point method and the area method. The results obtained by using the line method are slightly non-conservative, but still good. And this is the usual error interval we target when we use the TCD, and this is true independently of the considered value for the displacement rate. So, conclusion, we can use the TCD to model this situation. We can take into account the presence of geometrical features in concrete. The TCD critical distance was seen to approach the average interaggregate distance, which is good news because we can clearly see the physical meaning for L in this case. And finally, we got the best results by applying the TCD in terms of the point method and area method. Thank you very much.